Okay, so hi everybody, welcome back. Today we're going to be continuing our chapter 35 lecture on diffraction and polarization of light. And so the next topic to get into here is intensity in diffraction and interference patterns. So think back to the previous chapter, chapter 34. We spent a lot of time talking about the double-slit experiment. So if you send light through a pair of narrow slits, what comes out is the interference pattern. And we can project that interference pattern onto a screen. And what it looks like is a series of bright and dark spots that you'll see on the screen. And we came up with some equations to describe where those bright and dark spots will be located in the interference pattern. In a similar way, earlier in this chapter, chapter 35, we talked about single-slit diffraction. So this is where we send light through a single slit rather than a double slit, and we project that light onto a screen. So the details of the pattern are a little different, but it's also a series of bright and dark spots that get projected onto a viewing screen. And we also came up with some equations that describe where those bright and dark spots will be located when it comes to the diffraction pattern. So what we want to do now is take this a step further. We want to say something about the intensity of the light in those patterns. So how bright is the light at different locations in a diffraction and an interference pattern? That's what we want to be able to calculate in this section here. So in order to develop the equations that we're going to be using, we're going to use phasor diagrams. Okay, so phasor diagrams will be an important part of what comes next. So if you remember, the setup for a single-slit diffraction experiment looks something like this. We have a slit screen, so it has a single narrow slit where light can go through on that screen. And then we have a viewing screen over here. So light goes through the slit, and then we project it onto the viewing screen. Now the assumption is always that we have coherent light waves going through the slit. So you can imagine something like a laser beam going through the slit. And if we want to predict how the light waves will move after going through the slit, we can use Huygens' principle. Because according to Huygens' principle, each point on the slit can be considered a source of a spherical wave that moves outwards away from the slit. So here's a point on the slit. That will be the source of a spherical wave. So we draw the wave fronts like this, and it's moving outwards towards the viewing screen. Same deal with this point. That's the source of a spherical wave moving outwards. And same for every single point on the slit. So the reason we get this diffraction pattern with bright and dark spots is because those waves are sometimes interfering with each other constructively. So when you have constructive interference, you get a bright spot. Other times, they interfere destructively, which is where you get a dark spot. Okay, and that's overall what causes the diffraction pattern. So again, what we're trying to do here in this section is figure out some way of describing the intensity of the light at different points on the screen. Notice how the intensity is the greatest at the very center of the pattern, and it appears to get dimmer, less intense as you go out from the center. So we want to see why that is. Okay, so here's how we're going to set this thing up. First, we have a slit, and the width of that slit is A. So from one end of the slit to the other, the distance is A. We're going to divide that distance into n evenly spaced points. Okay, so we're going to put a bunch of points along the slit that are evenly spaced. There will be a total of n of those. So n could be 10, it could be 100, however many points you want to divide the slit into. The important thing to remember is that each one of those points can be considered to be the source of a wave. So this point is emitting a wave that goes out, so is this point, and so on. All of those points are emitting waves that eventually hit the viewing screen. So the distance between two neighboring points is going to be d, and d is just equal to a divided by n. We're taking the overall distance, dividing by the number of points. That's how we get the distance between 2 points. And so let's show the outgoing light rays that are going from the slit to the viewing screen. Now, just to be clear, here's what you're seeing. You're seeing light rays emitted from each point on the slit, which are going to a certain point on the viewing screen. So all of these rays are going to come together once they hit the viewing screen. Now, here's the thing to remember about the different distances involved in this problem. L represents the distance between the slit screen over here and the viewing screen where we project the light onto. The viewing screen is not even shown in this diagram, but L is that distance. And typically L will be a meter or maybe even a few meters. That's the basic order of magnitude for L. Whereas A is the width of the slit. That's going to be tiny in comparison to L. That's going to be typically much less than even a millimeter. So it's safe to say that L is much, much bigger than A. And for that reason, these rays that are going from the slit to a point on the screen can be considered basically to be parallel to one another. So these outgoing rays that are going to a certain point on the screen are basically parallel to one another. Okay, the other thing to note is that these outgoing rays make a certain angle with respect to our center line, and that's what we always call theta. Okay, so next, let's consider the path length difference between two successive waves that are hitting the viewing screen. So if I emit a wave from this point on the slit, and there's also a wave being emitted from this neighboring point on the slit, they travel different distances to get to the same point on the viewing screen. And so if we compare these 2 points on the slit that are emitting waves and traveling towards the viewing screen over here, we can see that the wave emitted a little bit lower on the slit over here has to travel a slightly greater distance than this point over here. So that extra distance is what we call delta x, or the path length difference between the two waves. So now let's find a way to calculate delta x, or come up with an expression for delta x. So first of all, notice that we've basically constructed a right triangle here. So let me actually put that triangle on the screen. D is the long side, that's the hypotenuse. Delta x is this side. Here we have a right angle. And up here we have the angle theta, which is the same angle that we see over here. Okay? So if we apply the sine function, sine of theta is opposite over hypotenuse. That would be delta x for the opposite side and d for the hypotenuse. So what that gives us is delta x is equal to d sine theta. So that should look familiar. This is something we came up with for the double slit interference pattern for delta x. So next, I want to remind you of a result that we derived back in chapter 34. If you have two waves that are in phase at a certain point, but then they travel different distances to get to another point, the phase difference between them is going to be k times delta x. Okay, the wave number k times delta x, which is the path length difference. That will give us the phase difference. So in this derivation, we're going to call that phase difference between the two successive waves delta beta. Okay, so that phase difference delta beta is k times delta x, where k is the wave number and delta x is the path length difference. So in this case, we have delta x is equal to d sine theta, as we just saw, and k is equal to 2 pi over lambda. That's just the definition of k. So that gives us delta beta is equal to 2 pi divided by lambda times d sine theta. But let's also remember that d, which is the distance between neighboring points on our slit, is just equal to a, which is the width of the slit, divided by n, which is how many points we divided the slit into. So now that gives us 2 pi times a times sine theta on top, divided by n lambda on the bottom. That's the expression for the phase difference. Now, let's take a look at a very simple case. theta is equal to 0. If theta is equal to 0, we're talking about the very center of the viewing screen, okay? And so if theta is equal to 0, sine of theta will also be equal to 0, and then delta beta will end up being 0. That means all of the waves arriving at the screen are perfectly in phase. There is no phase difference between them. So now let's draw a phasor diagram of that situation. So basically, we have a wave coming from the first point with amplitude A1. And then we have another wave coming from the second point with amplitude A2, but there's no phase difference between them, so I show 0 angle between these two phasors. And then the same for A3, pointing in the same direction, and so on. And so the total amplitude is going to be represented by a phasor pointing straight to the right. It goes from the start of our first phasor to the end of our last phasor. So this is A total right here, the total amplitude. Now, we're typically going to be assuming that all of these individual amplitudes, A1, A2, A3, are equal. So if I want to know what A total is, in this case, it would just be the length of each arrow, which is A, times the number of arrows I have, which is N. So in this case, A total is just N times A. And if you think about it, this is the largest possible amplitude we can get for A total, because all of the waves are perfectly in phase. They're perfectly constructively interfering with each other, okay? In other words, at the very center of the screen, we're getting a bright spot where the intensity is at a maximum. So what happens then if we're not talking about the exact center of the screen, but some other point in the diffraction pattern? In this case, delta beta, which is the angle between our phasors, is not necessarily going to be 0. In other words, there will be a phase difference between these different waves, and we'll have to account for that. So here's how the phasor diagram will look in general. We draw the first phasor. It's an arrow with length A. Now the next one is not necessarily going to be pointing in the same direction, so we'll show that there's an angle between them, and that angle is delta beta, the phase difference between the two different waves. And then when we draw the next phasor, again, there's an angle between that and the previous one, which is delta beta. And then again, there's an angle delta beta between that one and the next phasor. So what you see happening is the phasors are kind of curving around like this. Each time we add a phasor, we change the angle by an amount delta beta. So the total amplitude is going to be a phasor that goes from the start of the first phasor to the end of the last phasor like this. That's our total amplitude for our phasor diagram. Okay, so there are a few things to note about this diagram. First, if we have 4 phasors, so I have 1, 2, 3, 4 here, it just looks like a bunch of line segments connected end to end like this. But if we make n bigger, let's say we have 100 phasors, this is going to start to resemble not a bunch of line segments connected end to end, but more like an arc on a circle. Okay, so the more phasors we have, the more this begins to resemble an arc on a circle. It looks like a curve rather than a bunch of line segments connected end to end. In fact, if n goes to infinity, we have an infinite number of these phasors, then they will actually form an arc of a circle. Okay, that's the shape that this will end up becoming in the limit where n goes to infinity. Another thing to note is that since we have an arc of a circle in our phasor diagram, we can actually have the phasors form a complete circle. They can actually wrap all the way around back to the start. And if that's the case, then the total amplitude is going to be 0. Okay, so in the case where the phasors wrap around to form a complete circle, the total amplitude is 0, in which case we have a diffraction minimum. That's where we see the dark spots with 0 intensity. Okay, so how can we quantify that idea? Well, the angle between the first phasor in our diagram, which is shown here, and the last phasor, which is shown here, so what is the angle between this and this phasor. We'll call that beta, okay? So beta is equal to n times delta beta. The idea is to get from here to here, you have to increase the angle by a certain amount, which is just the number of phasors you have times the angle we increase by for each one of those phasors. So it's just n times delta beta. Okay, that would be the angle between the first and the last phasor. So if beta is equal to 2 pi, then you've basically wrapped around in a complete circle. If it's equal to 4 pi, you've actually wrapped around twice. If it's equal to 6 pi, you've wrapped around 3 times. But in each one of those cases, you have a diffraction minimum, okay? So that's how we know where the points of minimum intensity will be located. So let's work this out. The single-slit diffraction minima are going to be located at points where beta is equal to 2 pi, 4 pi, and so on, right? And again, beta is equal to n times delta beta. So we have n times delta beta, which is 2 pi times a times sine theta over n times lambda. We worked this out previously. So notice how n just goes away. N is completely irrelevant. It doesn't matter how many phasors you choose. Beta is always going to be equal to 2 pi times a times sine theta over lambda. And so again, if that beta is equal to 2 pi, that means the phasors have all wrapped around on themselves to form a complete circle. If it's equal to 4 pi, they've wrapped around on themselves twice for 2 complete circles. If it's 6 pi, they've wrapped around on themselves 3 times for 3 complete circles. In any of these cases, what you have is a diffraction minimum, where the intensity is actually 0. So what we can say in general is beta is equal to 2 times m times pi at the location of these diffraction minima, where m can be 1, in which case beta is equal to 2 pi, m can be equal to 2, beta is equal to 4 pi, m can be equal to 3, beta is equal to 6 pi, and so on. But notice m equals 0 doesn't work here. Okay, that's important to remember. M is just 1, 2, 3, and any integer above that. Okay, so let's apply that condition. We have beta, which is equal to 2 pi times a times sine theta over lambda, equaling 2m times pi. So immediately we can cancel out the factor of 2 and a factor of pi on both sides. And then let's just move the lambda over here. That gives us a sine theta is equal to m times lambda, for m equals 1, 2, 3, and so on. This is where the equation from the first video came from. Okay, this is where the diffraction minima are located. This is how we know this actually works. Okay, so we've derived an equation that we saw earlier. Now let's derive a new equation, which describes the intensity in this single-slit diffraction pattern. And so remember, this is what the phasor diagram will look like, generally speaking. Each phasor is an arrow representing a wave coming out of a certain point on the slit. Now, in the limit where we have an infinite number of points on the slit, we'll have an infinite number of phasors here to add together, and they'll begin to form an arc on a circle in the limit where n goes to infinity. The total amplitude of all of those phasors is represented by an arrow going from the start of the first phasor down here to the end of the last phasor up here. So this is the total amplitude represented by this black line. So what we're going to call that is a theta. That would be the total amplitude of the waves at a point on the screen that's an angle theta from the center. Okay, so we're not talking about the center of the screen, we're talking about some other location. So we'll call that a theta. Now, A0 would be the total amplitude of the waves at the very center of the diffraction pattern. And remember, this is the biggest possible amplitude we can get. When we're at the very center of the diffraction pattern, the phasors actually just form a straight line, okay? And the total amplitude ends up being A0. Well, all we're doing in this red curve is we're taking that same distance A0, but instead of having a straight line, we're bending it into the arc of the circle that you see here. So this is how we can graphically represent the amplitude of all of the waves, the total amplitude at some angle theta, and the total amplitude of all of the waves at the very center of the screen at theta equals 0. Okay, so we can basically work out what the relationship between those amplitudes is if we just do a little bit of geometry. So here's the next thing we'll do. Since this is an arc of a circle, we'll call the radius of that circle r. So this will be the very center. And the angle between the start of our phasor diagram and the end is beta. Okay, that's the same beta we saw earlier. The angle between the first phasor and the last phasor. That's the angle that we see cut out of the circle here. So A0 is an arc length. So we can calculate that arc length just by multiplying the angle beta times the radius r. So A0 is beta times r. Okay, the angle times the radius gives you the arc length. Now, we can use that to solve for r. So the radius of our circle would therefore be A0 divided by beta. And we can also construct a right triangle from this diagram. So notice how we have a large triangle here formed by the side lengths r, r, and a theta. If I cut that down the middle like so, okay, then I'll have an angle beta over 2 here, and then I'll have a side length a theta over 2 here when I cut the triangle in half. And this side length will still be r, and then this will be a right angle over here, okay? So by applying the sine function to this triangle, remember, sine of this angle is just the opposite side over the hypotenuse. The opposite side is a theta over 2. The hypotenuse is r. So that gives us sine beta over 2 is equal to a theta divided by 2r. And we can take that and solve for r. So r is equal to a theta divided by 2 divided by sine of beta over 2. Okay, so that's another expression for r. So I can set this expression for the radius equal to this expression for the radius, which is going to give me a0 divided by beta equals a theta over 2 divided by sine beta over 2. So what can we do with that? We can solve for the ratio of those amplitudes. A theta divided by a0 is equal to sine beta over 2 divided by beta over 2. That's what we get when we just arrange this to solve for the ratio of the two amplitudes. Okay, so we're getting somewhere. We have a statement about the amplitudes. We can turn this into a statement about the intensities by remembering that the intensity of a wave is always proportional to its amplitude squared. I is proportional to amplitude squared for any type of wave. So we can equivalently say that I divided by amplitude squared is a constant, okay? In other words, I0 divided by A0 squared, that would be the intensity at the very center of the diffraction pattern divided by the amplitude squared there is equal to I theta, so the intensity at some other point on the diffraction pattern divided by A theta squared like this. So to rearrange that, we have I theta, the intensity at any angle theta in the pattern, is equal to I0 times A theta over A0 squared. But here's the thing, we know that ratio of the amplitudes already. So that's going to be I0 times sine of beta over 2 divided by beta over 2 all squared. So I can actually use this to get the intensity at some angle theta if I know the intensity at the very center of the pattern, and then I know this beta quantity here. So to summarize, this is our result. I theta is equal to I0 times sine of beta over 2 divided by beta over 2 squared. I0 is the intensity at the very center of the diffraction pattern, again, where theta is equal to 0. I theta is the intensity of the light hitting the viewing screen at any other angle theta. Now beta, remember, is the phase difference between the first and the last phasor in the diagram. That would represent the phase difference between the wave coming out of the very top of the slit and the wave coming out of the very bottom of the slit. That's what it represents. But it's equal to, as we worked out, 2 pi over lambda times a sine theta. So that's what goes in here for beta. So we have everything we need to calculate intensity. It's all given here. And so real quick, I'm going to show you what it looks like when we plot this function out, because it's kind of complicated. It might not be immediately obvious what the function looks like when we plot it out. So on this axis, we have I as a function of theta. And on this axis, we have the angle theta. So theta equals 0 is right in the center of the diffraction pattern. And as we go out, we're going further away from the center. So the first thing to note is we have a very strong peak in the very center. This is the central bright spot where the intensity is at its maximum. Then right next to that, it goes to 0. So we have a minimum in intensity on either side of that. Then we have another peak, but it's a much smaller peak, but it's another intensity maximum, then another minimum, then another maximum. And notice how the intensity maxima are getting smaller. So there's still a bunch of bright spots, but they're getting dimmer as we go out away from the center. So I'm not going to prove this, but it turns out about 90% of the total light energy is contained in that central peak. So this is by far the brightest part of the pattern. 90% of the energy is contained here. All of the rest is in the fringes. Okay, so I want us to take a closer look at the equations we've derived and consider some special cases. Okay, so first, what happens when beta is equal to 0? Well, if beta is equal to 2 pi over lambda times a sine theta, the only way for beta to equal 0 is if theta is equal to 0. So in other words, we're talking about the very center of the diffraction pattern. Well, this is a little tricky because we have sine of 0. Sine of beta over 2 is sine of 0, which is 0. But we're actually dividing that by beta over 2, which is also equal to 0. So just by directly plugging in beta equals 0, you're going to get an indeterminate form. You're going to get 0 divided by 0. So we're going to have to do a little bit of extra work to see how that works out. But we'll show that I theta goes to I0 when beta goes to 0. Okay? We're also going to show that the intensity goes to 0 whenever we have sine beta over 2 equals 0, but beta is not equal to 0. Remember, if beta is equal to 0, we get this indeterminate form. Okay? So in other words, if beta over 2 is equal to pi, then when you plug in sine of pi, you get 0. So that works. If beta over 2 is equal to 2 pi, okay, you plug in sine of 2 pi, you get 0, 3 pi works, 4 pi, and so on. That's where we get 0 intensity, okay, because the top of this fraction goes to 0 and the bottom doesn't. So this will lead to our previous result for where the single-slit diffraction minima are located, where the points of minimum intensity are located. We're going to show that we get the equation a sine theta equals m lambda for m equals 1, 2, 3, and so on. So basically, this result we derived using phasors also contains the result that we saw earlier for where the diffraction minima are located. So let's see how this all works out. Okay, so again, we have I theta equals I0 times, in brackets, sine beta over 2 divided by beta over 2, all squared, where beta is equal to 2 pi divided by lambda times a sine theta. Now, in the very center of the screen, the center of the diffraction pattern, again, that's where theta is equal to 0, which implies beta is equal to 0. what we have is an indeterminate expression, because if we look at the thing in brackets, let's call it f of x, which is equal to sine of x divided by x. So x in this case is going to be beta over 2. So in brackets we have sine beta over 2 divided by beta over 2. I'm just going to write that more simply as sine x divided by x. We want to know what happens as x goes to 0. Well, since we have sine x, which when you plug in x equals 0 gives you 0, divided by x, that's an indeterminate expression because it's 0 over 0. So in order to take the limit as x goes to 0, we need to apply L'Hopital's rule, which means we take the derivative of the expression on top, so the derivative of sine x, divided by the derivative of x. So the derivative of sine x gives us cosine x. The derivative of x gives us 1. And so when we plug in 0 for x, we have cosine 0 divided by 1, which is just 1 divided by 1, or 1. So we have I theta equals I0 times 1 squared. That proves the result we were trying to show, that I theta is equal to I0 at the very center of the screen. Okay, so next, let's take a look at the diffraction minima. This is where I theta is equal to 0, no intensity. And if we go back to the original expression, the only way for the intensity to go to 0 is if sine beta over 2 goes to 0, but beta over 2 is not 0 because we don't want this indeterminate expression of 0 divided by 0. So basically we're going to say sine beta over 2 is equal to 0, okay? Which means beta over 2 can take on a range of values. It can be pi, it can be 2 pi, it can be 3 pi. Sine of any of these angles will be 0, but not 0, okay? We don't want beta over 2 to equal 0. Okay, cool. So we can more generally write this as beta is equal to 2 pi, 4 pi, 6 pi, and so on. Just multiply the 2 all the way through, which we can say is 2m pi for m equals 1, 2, 3, and any integer. Okay, that's how we can generally refer to the values of beta that give us a diffraction minimum. But remember, beta is equal to 2 pi divided by lambda times a sine theta. And if we set that equal to 2m times pi, we can cancel out 2, we can cancel out pi, and we get a sine theta is equal to m times lambda for m equals 1, 2, 3, and so on. So these are the locations of the diffraction minima. Okay, so that's where that formula we saw in the previous video actually comes from. So let's do an example problem where we get to put these results to use. So we want to estimate the intensities of the first two maxima next to the central maximum in a single slit diffraction pattern. We're not going to give a number, we're just going to give the answer as a fraction of I0. So remember, I0 is the maximum intensity at the very, very center of the screen. That's our central maximum. Then m equals 1 is the next maximum. We have a peak over here. Then we have the m equals 2 maximum over here. And the intensity is not the same. It's a much lower intensity at these m equals 1 and m equals 2 maxima. What we're going to do is estimate what those intensities actually are relative to that central intensity. Okay, so let's work this out. So remember, the diffraction minima, these occur whenever A sine theta is equal to m times lambda for m equals 1, 2, 3, and any integer beyond that. What about the diffraction maxima? Because we're interested in the peaks of intensity. Well, to get it exactly right, this is what you'd have to do. You'd have to take our expression for intensity and take its derivative and set that equal to 0, because wherever the derivative is equal to 0, you have a maximum or a minimum. So if we want to find the maxima, we could do this and then solve for theta. That would tell us where the peaks are. But we can make an approximation which is much easier to work with, and that is a peak in intensity is going to be roughly halfway between two minima of intensity, right? So if you have a peak of intensity, on either side of that you have a minimum like this. So we can say A sine theta is not just an integer times lambda, but a half integer times lambda, m plus a half times lambda. Again, m taking the values 1, 2, 3, and so on. Okay, so that's easier to work with, and it works pretty well, so let's go with that. So remember, beta is equal to 2 pi over lambda times A sine theta. So therefore, beta over 2 is just that same expression, but cancel out the factor of 2 on top. And remember, if we apply the approximation I just wrote down, this will give us beta over 2 is approximately equal to pi divided by lambda times this. This is what we can sub in for A sine theta. So m plus a half times lambda, cancel out lambda. In other words, we have pi, we have pi times m plus a half at the diffraction maxima. Okay? So beta over 2 is approximately equal to pi times m plus a half at the diffraction maxima. So if we're talking about the m equals 1 max, then beta over 2 is just going to be pi times 1 plus a half, or 3 halves pi. At the m equals 2 maximum, beta over 2 is going to equal 2 plus a half times pi, which is 5 halves pi. Okay, so we can actually just plug those into our formula for intensity, which is I theta equals I0 times sine beta over 2 divided by beta over 2 squared. So for m equals 1, we have I theta equals I0 times sine of 3 pi divided by 2 divided by 3 pi divided by 2 all squared. All right, well, sine of 3 pi over 2 is actually minus 1, but we square it, so it's just 1. And this gives us I0 times, we have 3 pi over 2 on the bottom, so that would be the same as 2 divided by 3 pi on top, which we square. So that's I0 times 4 divided by 9 times pi squared, which is approximately equal to, if you crunch the numbers, 4 divided by 9 pi squared is about 0.045 I0. So only about 4.5% of the intensity at the center. And then if m is equal to 2, then we have I theta equals I0 times sine of 5 pi over 2 as before, divided by 5 pi over 2 on the bottom, all squared. That's going to be I0 times 2 divided by 5 pi all squared, because the sine term just goes to 1. So this would be I0 times 4 divided by 25 pi squared. And again, if you crunch that number, it turns out to be about 0.016 times I0. So at the first peak from the center, the intensity is only about 4.5% of what it is at the center. The second peak from the center, it's only about 1.6% of what it is at the center. All right, so next, let's take a look at the intensity in a double-slit interference pattern. So remember, back in chapter 34, we talked about the double-slit experiment. If you send light through a pair of slits, after that light comes out of the slits, it will produce an interference pattern, a pattern of bright and dark spots that you can project onto a screen. What we want to do is be able to calculate what the intensity of the light is in that interference pattern. So the first thing to remember is that all the way back in chapter 34, when we were doing the derivation for the double-slit interference pattern, we found that the phase difference between the two waves coming out of the slits is given by k times delta x. So it's the wave number times the path length difference delta x. Let's call that phase difference delta. Okay, so this is a lowercase delta. So delta is k times delta x. K is equal to 2 pi divided by lambda. That's just the wave number. And we solved for delta x, and we found that it was equal to d sine theta, where d is the distance between the two slits, and theta is the angle of our outgoing rays relative to the center line. Okay, so we have delta, phase difference between the two waves, is equal to 2 pi over lambda times d sine theta. So this was all given back in chapter 34. But let's take a look at what the phasor diagram would look like if theta is equal to 0. So if theta is equal to 0, then sine of theta is equal to 0, and we get delta is equal to 0. In other words, we have two phasors, one for this slit down here, another one for this slit up here, and there's 0 phase difference between them. So for the first one, I'll draw an arrow with amplitude A. For the next one, it's an arrow with amplitude A, and they're pointing in the same exact direction. So the overall amplitude would just be 2 times A. Okay, so what we'll say is A0, the amplitude at the center of the screen, is equal to 2 times A, which is the individual amplitudes for the two slits. Okay, if we use any other angle besides theta is equal to 0, then there will be some kind of phase difference between the two waves. So we'll have the first phasor pointing in a certain direction. Let's say it's pointing to the right. The next one will be pointing in a different direction. And the angle between them, again, is this delta that we calculated over here. So then the net amplitude is a phasor that goes from the start of your first phasor over here to the end of your second phasor over here, and we'll call this A theta. So it's the amplitude at some angle other than 0, okay? So let's relate A0, the amplitude of the waves at the very center of the screen, to A theta, the amplitude at some other angle. And the way we'll do this is by cutting this triangle in half. So we'll drop a line that cuts the triangle exactly in half this way, so that on this side, I'm going to have A theta divided by 2. And on this side, I'm going to have A, just the amplitude of one of those waves. But remember, the amplitude of one of those waves is A0 divided by 2. Okay, so in other words, I can replace this side length, which is A, with A0 divided by 2. And then I'll have a right angle over here, and then this angle will end up being delta divided by 2. So it's this angle delta divided by 2. Okay, so if we analyze that triangle, this time we'll use the cosine function. We'll note that cosine of any angle is just the adjacent side divided by the hypotenuse. In this case, the angle we're talking about is delta over 2, so cosine of delta over 2 is equal to the adjacent side, which is a theta over 2, divided by the hypotenuse, which is a0 over 2. Just cancel out those factors of 2, you get a theta divided by a0. So remember, when it comes to intensity, that's proportional to the amplitude squared. So just like we did in the previous derivation, we can say intensity divided by amplitude squared is constant, meaning I0, the intensity at the very center of the screen, divided by A0 squared is equal to I theta, the intensity at some other point on the screen, divided by A theta squared. Okay, so that ratio stays the same, so we can relate the two like this. And if we solve for I theta, that gives us I0 times A theta divided by A0, all squared. So the ratio of the amplitude squared, but we know what that is. That's cosine delta over 2. So we have I theta is equal to I0 times cosine delta over 2 all squared. So that's how we describe the intensity in a double-slit interference pattern. Okay, so to summarize the result we just derived, we have I theta is equal to I0 times cosine delta over 2 all squared, where this angle delta is the phase difference between the two waves coming out of the slits. So delta, as we found, is equal to 2 pi over lambda times d sine theta. Now to be clear, this result strictly applies to double-slit interference where we ignore diffraction of the light going through the slits. We know that if light goes through a narrow slit, you'll have this effect called diffraction. So we're ignoring that effect in this result here. We'll see how to include diffraction later on. Okay, so if we plot this function out, we have I theta on the vertical axis and theta on the horizontal axis. We see that I0 is the maximum of our function. And we actually reach that same maximum multiple different times. So at the very center of the screen, we're at that maximum value. We dip down to 0 intensity, go back up to that maximum value, and then back down to 0 intensity in an alternating pattern. Again, this is just the pattern of bright and dark spots that you see on the screen. When the intensity is at a maximum, that's a bright spot. When it's at 0, that's a dark spot. So we can show using this result that the interference maxima, where again I theta is equal to I0, those occur whenever d sine theta is equal to m times lambda. And then the interference minima, where I theta is equal to 0, those occur where d sine theta is equal to m plus a half times lambda, where m can be 0, 1, 2, and so on. So all the integers, 0 is included. So we derived this way back in chapter 34, both these equations, but I'm going to show you how we can get these results from this result for the intensity. So let's go through that. So we'll start with the results that we derived. I theta is equal to I0 times cosine delta over 2 all squared, where delta in this case is equal to 2 pi divided by lambda times d sine theta. Now, if we want to use this to figure out the locations of the interference maxima, these are positions on the screen where the intensity is equal to I0, that's the maximum intensity. Well, the only way for this to work basically is if cosine delta over 2 squared is equal to 1. Okay, if that's the case, then I theta is equal to I0. So we'll square root both sides to give us cosine delta over 2. Well, the square root of 1 is plus or minus 1. We have to account for both the positive and negative solutions here. So the question is, what angle delta over 2 will give me plus or minus 1 if I take the cosine of it? Well, 0 works, because if I take cosine of 0, I get 1. Pi works, because if I take cosine of pi, I get negative 1. 2 pi also works, 3 pi, and so on. So that means delta is equal to 0, 2 pi, 4 pi, 6 pi, and so on. Meaning delta is equal to 2m pi, where m can be 0, 1, 2, and so on. Okay? So if we take our expression for delta, which is 2 pi over lambda times d sine of theta, and set that equal to 2m pi, cancel out the 2, cancel out the pi, and then take the lambda over to the other side, gives us d sine theta equals m lambda. Again, m is 0, 1, 2, and so on. Okay, these are the maxima. That's what we found back in chapter 34. The minima are going to be points where the intensity goes to 0. So if we go back to our original expression, the only way for the intensity to go to 0 is if this cosine delta over 2 squared term goes to 0. So we have cosine delta over 2. As long as that's 0, then we have 0 intensity. And so the question then becomes, what angle delta over 2 gives me 0 when I take the cosine of it? Well, pi over 2, cosine pi over 2 is 0, 3 pi over 2, 5 pi over 2. These are the possibilities. But if I just want delta, then I multiply all that by 2. That would be pi, 3 pi, 5 pi, and so on. Basically the odd multiples of pi as opposed to the even ones. So generally, we can write this as 2m plus 1 times pi. That's the sort of general way of saying I have an odd multiple of pi. Of course, m can be 0, 1, 2, and so on. So plug in delta, that's 2 pi divided by lambda, times d sine theta. We're saying that is equal to 2m plus 1 times pi. So we'll cancel out the pi's. And we'll say d sine theta equals, if I divide through by 2, I'm going to have m plus a half instead of 2m plus 1. And then if I take the lambda over to the other side, it's right next to that term. So d sine theta is equal to m plus a half times lambda, where m is equal to 0, 1, 2, and any integer. This is where the minima are occurring. And again, we found that back in chapter 34, but this is how we can see it using this new method. Okay, so here's one for you guys to try out. A laser beam with a wavelength of 535 nanometers is directed towards a pair of narrow slits, which are separated by 0.525 millimeters. The interference pattern is projected onto a screen, which is 1.25 meters away from the slits. The intensity of the light at the very center of that interference pattern is 135 watts per square meter. The question here is, what is the intensity of the light at a point on the screen that is 1.25 centimeters away from the center of the interference pattern? So we're going to ignore diffraction, which means we can just use these results that we derived just a second ago. So pause the video, see if you can work this out, and then come back to it when you think you have your answer. Okay, so we'll start by drawing a picture of what's going on here. Here's the slit screen, where the distance between the two slits is d. And then some distance away from that is the viewing screen. And let's draw the center line like this. And the distance between the two screens will indicate as L. So we're interested in what's going on the screen a certain distance away from the center, which will indicate as Y on our diagram. So we can also locate a point on the screen with an angle. The angle off the center line is always theta. So in our equations, that's the angle theta that's being referred to. Well, we can solve for the angle theta because, of course, tangent is equal to opposite over adjacent, where in this case, the opposite side is y and the adjacent side is L for the angle theta. So theta should just be the inverse tangent of y over L. In this case, you have values for both of these. Y is 1.25 centimeters, so 0.0125 meters. And then L is 1.25 meters. So the angle, if you work it out, is 0.5729 degrees. We'll keep 3 sig figs on that. Okay, so that's useful because we can then calculate delta. Remember, delta is 2 pi divided by lambda times d sine theta. So if we calculate delta, let's do that down here. Delta is going to be 2 pi divided by lambda, which is 535 nanometers, or 10 to the minus 9 meters. And then we have d, which is 0.525 millimeters, or 0.525 10 to the minus 3 meters. And then we'll take sine of the angle we just found, which is 0.5729 degrees. Okay, so crunch those numbers, and here's what you get. Turns out to be 61.65. And this is a little tricky, but to be clear, the units are radians. This 2 pi factor sets the unit to be radians. The units of meters cancel out. And then, of course, sine of anything is just a unitless number. So this is in radians. And the reason we can use this is because I theta is equal to I0 times cosine delta over 2 squared. So I0 is the intensity at the very center of the pattern, which is 135 watts per square meter, 135 watts per square meter. So that multiplies cosine of delta over 2, so 61.65 radians over 2, and then that whole thing is squared. Okay, so when you calculate the cosine, remember that the angle you're putting in is in radians here. But if you do that, what you'll get is 93.1 watts per square meter. So that's the answer. We were able to calculate the actual intensity at a specific point on the screen using the result we derived. So when it comes to the double slit experiment, there are actually a combination of 2 different things going on. So the light waves coming out of the 2 slits will interfere with each other. So we'll get this interference effect between the 2 different light waves coming out of the 2 different slits. But also remember that if light goes through a narrow slit, it diffracts as it goes through that slit. So you're going to have this combination of interference and diffraction, and in order to get it right, you're going to have to account for both. Fortunately, we've already derived a formula for the intensity in a diffraction pattern. We also derived the intensity in a double-slit interference pattern. We can simply combine those two results to get the overall effect. So I theta, the intensity on the screen at some angle theta, is equal to I0, which is the intensity at the very center, times sine of beta over 2 divided by beta over 2, all squared. This is what we call the diffraction factor, okay? This is due to the diffraction. But then we multiply that by cosine delta over 2 squared. This is what we call the interference factor. Now remember, beta in this equation is 2 pi over lambda times a sine theta. And then this delta over here is 2 pi over lambda times d sine theta. So that's kind of a lot to put into one equation, but hopefully you understand what all the different parts are. Okay, so this is what the result looks like when we plot it out. So we'll start at the top. This is a single slit diffraction pattern. So this is what it would look like if you sent light through a single slit and projected that light onto a screen. You would see the intensity as a function of the angle from the center change like this. So at the very center, where the angle is equal to 0, you have the highest peak in intensity. That drops down to a minimum, and then another peak in intensity, but it's a much smaller peak, and then another minimum, and then another peak in intensity. And in the diffraction pattern, the peaks in intensity get smaller as you go further out from the center. Now, if we have a double-slit interference pattern, it works a little bit differently. Of course, we have a peak in intensity at the very center, and then that goes to a minimum, and then we go right back up to that same exact peak in intensity, back down to a minimum, and so on. So if it's purely interference with no diffraction, then we keep hitting the same peak in intensity over and over again, and it actually doesn't get smaller. But when we combine these two effects, which is what we have to do to get it actually right, to have a double-slit interference pattern while accounting for diffraction, well, the way you can think of this is we have this curve enveloped by this curve. So in other words, we still have this rising and falling of intensity as shown by the double-slit interference pattern, but the peaks are going to be modulated by this first curve over here. So you can imagine that that first curve is enveloping the second one like this. So, and in fact, the peaks in intensity do get smaller as you go out, okay? That's the overall effect of double-slit interference with diffraction. And I want to point out something in particular about this graph. You notice that where we have a diffraction minimum, it actually cancels out the interference maximum. So even though the interference pattern is peaking somewhere, if we're essentially multiplying that by 0, which is where our diffraction pattern is hitting a minimum, well then we'll have a minimum. So you'd expect to see a bright spot here normally, but it's actually missing from the interference pattern, okay? So that's what we call missing order in the double-slit interference pattern. It happens when a diffraction minimum overlaps with an interference maximum, okay? That's going to result in a missing bright spot in your interference pattern. So the idea is diffraction minima, these occur whenever a sine theta is equal to m times lambda for m equals 1, 2, 3, and so on. So those are points where the intensity goes to 0 in your diffraction pattern. But interference maxima occur whenever d sine theta is equal to m times lambda for m is equal to 0, 1, 2, and so on. And just to be clear, d represents the spacing between the two slits, and a represents the width of each one of the slits. Okay, so those are two different distances. Now, if we have a diffraction minimum overlapping with an interference maximum, well, 0 intensity is going to multiply a maximum intensity, but you'll still get 0. So you'll have 0 intensity which means you'll have a dark spot where you might expect to normally see a bright spot. So let's do an example. Light goes through a pair of slits which are spaced a distance d equals 0.60 millimeters apart. You notice that there are 11 interference maxima within the central diffraction maximum. The question is, what is the width of each slit? So again, the idea is you have a whole bunch of interference maxima, a whole bunch of bright spots within that central diffraction maximum. Based on that, we'll be able to calculate the width of the slit A. So let's work it out. So let's start by drawing the actual pattern. We have a very bright spot at the center. That would be the m equals 0 interference max. And then on either side of that, we'll have a bunch of other secondary maxima. And we're told that there is a total of 11 interference maxima within the central diffraction maximum. So we need a total of 11 of these. So if we have 1 in the center, we'll have 5 on either side of that. So here, 1, 2, 3, 4, 5 on this side, 1, 2, 3, 4, 5 on that side. And then, as soon as we get to the edge on either side of what I just drew, we reach the first diffraction minimum. So the first diffraction minimum would be m equals 1 for diffraction. And again, that's on either side. So basically, everything we just drew here is the central diffraction max. Okay, with the minimum on either side of it. Okay? So what this means is, right where we have that first diffraction minimum, we would expect to see m equals 6 interference maximum. But it's missing. Okay, it's missing because it lines up with the diffraction minimum. So just to be clear, we count m equals 0 at the center, 1, 2, 3, 4, 5 is what we actually see, and then m equals 6 is what's missing in the interference pattern. Okay, so that's the picture to have in mind. Now, we'll remember that interference maxima occur whenever d sine theta is equal to m times lambda. Okay, so here we're going to plug in m equals 6. D sine theta is equal to 6 times lambda, so sine theta is equal to 6 lambda over d. Now, diffraction minima. These occur whenever we have a sine theta is equal to m times lambda. So remember, for the first diffraction minimum, we're plugging in m equals 1. So I have a sine theta is equal to, I'll just put in 1 times lambda. Okay? So from this, we see that sine theta is equal to lambda over a. So here's how we solve for a. The m equals 1 diffraction minimum is aligned with, it lines up with the m equals 6 interference maximum. So in other words, the theta we're talking about in these two expressions is the same. So I have 6 lambda over d equals lambda over a. Doesn't even matter what lambda is, cancel that out. That gives us a equals d over 6. Okay? So to be clear what this looks like, if we have the slit screen, D is the distance between the two slits, but A is the width of each one of those slits. So what we're finding is that the width of the slit is just 1/6 of the spacing between the slits. So you have A equals 0.6 millimeters divided by 6. That's 0.10 millimeters, okay? So it's pretty simple to calculate once you see the concept behind it. Okay, so here's one for you to try out. We have coherent monochromatic light, which goes through a pair of slits, and then the interference pattern is projected onto a screen. The M equals 0, 1, 2, and 3 interference maxima are all present on the screen, but the M equals 4 maximum, that is the fourth bright spot from the center, is missing. So the question for you is, what is the ratio of the slit separation and the slit width? What is D divided by A? So here's the pattern. We have the central maximum, we have M equals 1, M equals 2, M equals 3, but M equals 4 is missing. So based on that, try to figure out the ratio of D divided by A. So pause the video, try to work it out, and then we'll go through it together. So the first thing to realize is that the M equals 4 interference maximum lines up with the M equals 1 diffraction minimum. And because of that, you don't actually see the interference maximum. It's a dark spot where you'd expect to see a bright spot. So again, for interference max, we have d sine theta is equal to m times lambda. Now here, we're saying m is equal to 4. So we have sine theta is equal to 4 times lambda over d. For the diffraction minima, we have a sine of theta is equal to m times lambda, where in this case m is equal to 1, because it's the first diffraction minimum from the center. Okay, so that means sine theta is also equal to lambda over a. These are both valid expressions for the angle we're talking about. So we can set them equal. Sine theta is equal to sine theta, giving us 4 lambda over d equals lambda over a. So d over a is 4. So it's a 4-to-1 ratio between, again, the spacing between the slits D and the actual width of the slits A. So D over A is a 4-to-1 ratio in this case. All right, so that's going to be it for this video. We'll continue on in the next one and wrap up chapter 35. So I'll see you then. But until then, as always, be safe out there, be healthy, take care.